too big, no? Huh? Page height, huh? Okay. Okay. So let's continue. All of you thought about this circuit? What was the circuit supposed to do? What was the circuit supposed to do? Diode shaping, right? Okay. So I think we left off by saying that this particular circuit finds use, or similar kind of circuits find use when you want to do shaping of, say, a triangle to a sine. That is difficult. Right, because what is happening? So Prasanna's question is here. If you look at the, if I'm trying to guess whether this is your question. So if you look at the, you look at this slope, okay? Then you look at that slope. Then you look at that slope. What's happening to the slope? The slope is decreasing, right? For each segment, for each progressive segment, the slope is decreasing, which means the resistance is, the way drawn here, V by I is the slope. So the resistance also is decreasing. So what you are doing here effectively is, for every segment, you are introducing a resistor in parallel. When you introduce a resistor in parallel, what happens to the resistance? It decreases, right? So now, instead of this decreasing, if there was a situation where after, say, one of these corner points, the resistance actually increased, can you accommodate it? It will be an interesting question to think about. So think about that. Okay, you didn't mean that. All right.
I meant the negative resistance.
Okay. That I don't think is possible, right? Further, taking that further, can you then? So what are we discussing? So same circuit. Let me just take that to the next page, and then it will become clear to others also. Okay, so let me just take that. Today's date is what? So what we are talking about is if in this particular circuit that's okay, yeah. Say now that I want okay, say first point which I raised, people stop murmuring, right? So instead of this particular resistance, or instead of this segment going like so, if I were to give you a situation where this resistance actually went, okay, let me take this segment. Instead of going so, if I were to put it like this, okay, so the resistance is actually increased. Can you accommodate this in the diode shape, that kind of circuit that we had? Okay, so think about that. Yes. Okay. But what if I am very nasty and I make, if I am every segment to be this kind of increasing resistance? Okay, so all of you think about it. So the problem is, if I want this kind of curve, how do you do it? We can take it later. I'll give it in the tutorial or something like that. Let's not too much time thinking about that right now. So this is problem A. Okay, and then problem which I think Prasanna alluded to is, if I want, for example, the same kind of thing, but say I want I want in one segment the resistance to actually be negative. Is it possible to have the resistance negative? That is that I want that in a particular segment. Is that possible? Rest with using whatever we have so far. Is that possible? Okay. So that's the second point which you will think about. I may discuss this in class, but just think, right? So the tutorial is ready. I'll check today. It will be 1 week from whenever I post it. Okay. So think about two situations. All right. Okay. Anyway, let's proceed. So I now want to convert, for example. So if I had some number, right? Diode shaping networks. Okay, we are still diode shaping networks. Okay. So say I want this kind of, and I mentioned we are looking at applications where we're going to convert a sinusoid into a triangle, right? Why do you think that's important? We mentioned this in class also. Shivang, why would you want to convert a sinusoid into a triangle? Oh, sorry, a triangle into a sinusoid. Yeah. So basically, if you want to generate a triangle, if you take a current source, right, and you put through a capacitor, correct? And say I'm just drawing this fun. Okay, so there is a switch, and say I have another current source here. Let me say that this is current source of value I0, okay, constant, and say this is a current source of 2I0, and say I'm interested in the voltage across this capacitor, okay, and say I switch, say I toggle this some periodic in a period manner, right? So say at t equal to, say the switch is closed, so what will happen? If the switch is closed, you can assume that I0 is charging this capacitor. So how will voltage change? Right? Voltage will increase, right? No. Assume at t equal to 0, this 2I0 is not there. Right? At time t equal to 0, assume only I0 is there. If I0 is there, then this will increase, right? And then say at time t equal to some say at t1, say I toggle this at time t1. So what will happen now? What will happen now? It will decrease, right? And what would be the rate at which decreases? Same rate, right? Because now what will happen is that you will have I0 going in and 2I0 going out. Effectively, what is going out? I0 is going out. So then this will you can think of a situation where I go from there to there, right? And then say I run this time t2. So from time t1 to t2, in this time let this be on. Okay, that is not a good I said on, and then that symbol is belongs to, but then it reads as 1. So let's remove that. Okay, this is on in this interval of t1 to t2. You will have now you will get a discharge now. Here, what am I plotting? I'm time, and here plotting voltage across the capacitor, right? And then this again would say go this way. Okay, so getting a sinusoid is actually fairly straightforward, right? In fact, there is an IC which does precisely this, and we will be getting this. It's a there's a waveform generator called 8038 which effectively does this in a slightly more complicated fashion, but it does this. Charge I0 discharges with 2I0, so basically you can get a triangle. Okay, so I want to take this triangle and convert it into a square. Sorry, not. If I want to convert it, what do I do? If I have a triangle and I want to convert it into a square, what should one? No, this is very straightforward. I have a triangle as input, I want to convert into a square. What is the device I should pass it through? We've done this. Differentiator. Differentiator. Okay, that's one choice. But even simpler thing. We just pass it through a comparator, right? If you pass it through a comparator, will that work? No, think about it. Right, so then, but you will get a different period. You will get a period. If I pass it directly through a comparator, then wherever it is positive, it will become positive, and then it will be that also, right? That's what you want. Right? That's the easiest way to convert this to a square. And maybe so comparators also are something that can be used, right? Okay. So now let me assume that. So the only difference in what we had yesterday and what we are drawing now is that in yesterday's plot the x-axis was what? Was in this plot both x and y axes are voltages. Okay. No, sorry. Or rather, you're interested in finally is a plot of voltage versus voltage. When you're doing the shaping, you will effectively look at voltage versus voltage. Okay, we'll come to that. I'm clear. Okay, so if I say this is 0, say this is 5, this is 10, 15, 20. Why is 20 a useful number? 20 seconds is 50 hertz. Right, so keep that in mind. So your power line frequency is 20 milliseconds. Okay, and say what is V0 in circuit? Good question. So basically you are taking VC, and then you are what I am thinking of doing is I am taking this particular VC, I am seeing it through block, and the out is this is your diode block, and the output, that is your V0. I want you to design this diode block. Okay, so say this is say 10 volts. Okay, and this is 5 volts, and somewhere here says 8 volts. Okay, and what you are interested in, say, is that from 0 to 5 I want to follow, and then I want to have this. Again up to 5, then 8. Okay, see, that's what I want as the output. Alright, so the output looks more like a sinusoid compared to the input, right? right? The output looks more like a sinusoid than the input, right? So if you can put more sections and get a smoother sinusoid if you so desire. So how do you think one should go about designing this? Huh? Okay. Okay. So maybe I'll draw the circuit and then you can fill in the values for this. Okay, it's very similar to what we had today. Yesterday, what did we have? Here the shape was in the curve looking at was I and V. Now we are looking at a curve where basically, if you were to draw this in another fashion, what you are essentially looking for is curve which basically up to 5, 10, 8, 5, 10, say this is V I and VO, okay, and let me say your VI for this diode block. This is the input and output, okay, that has to be the capacitor. But what am I interested in? The transfer function that I'm basically interested in here is that from minus 5 to 5, I basically want V out equal in, right, in this area. I want V out equal to V in here, here, here and here. And then from 5 to 8, or rather from Vi from 5 to 10, your output should go from on this, right? Right? And similarly for the negative side also, this is minus 5, and then you will have say a minus here somewhere, right? And say this is minus 5. Yes. Ideal current sources. Yes. The voltage drop across capacitor. Just think about that. No, in this particular situation. Okay, let's just think about that. Okay, what are you saying? You're saying that. Okay. Why? What is a current source? What is the voltage across a current source? No, what is the voltage across a current source? Ideal current source. It can be anything, right? It will be set by the other things in the circuit. The valid connection. Okay. All right. So this is what we want. Yes, Prakhar? Sir. Wait, because we want to draw like 10 elements now. Let's draw one, okay, and then it will become clear. Which one? Here. Why did I take on the negative side? Because I also want, now look at what the axes are over here. This is a transfer between V and VO. So you have a situation where Vi is negative, no? So you need to worry about that also. Correct? So just look at this circuit and see if it will give you what you want. Okay? So say I start with some R1. Okay, and well, maybe call this as R0. Okay, let's have an R1 diode and a battery, the usual circuit that we had earlier, right? And let me say I have another R2 diode and battery, and let me not put diode this way. Okay, so basically my V out is here, and your V in is here. So will this circuit give you what you want? What should be the values of the various resistors and batteries? But what should you have the various things as? Okay, if I put R naught equal to 1 kilo ohm, then do you need R0 there at all? R naught? R naught should be in parallel. But why do you need R naught? But look here, this is not a plot of V versus I. This is a plot of V versus V. Huh? Okay. All right. But up to 5 volts, right? 5 volts, what do you want to happen? V naught must be equal to Vi. Huh? R naught is not required.
Just want the diode to be off.
Okay. Now if R naught is not required, alright, then say both dials are off, V naught is equal to Vi. Okay, then you turn one on. What will happen to V naught and Vi if this R naught were not there? It will still be equal, right? So that means that should be there, right? So think about how you will design this. Okay, I'll leave it here. Alright, maybe R is there, maybe R naught is not there, maybe R is there, R1 is not there. Okay, this roughly this circuit should work, but you're going to think about other values. Okay, alright. Where? Alright. Which voltage source? This battery. Then you have to choose the value of the battery. And why do you want the battery there? My point is that if you have a circuit like this, if I have a circuit which is like no battery, okay, then say the diode is on in some region, and if say this Vi and this is, what is the relationship between V out and Vi for this? They are always equal, right? So this one will not work, no? It won't work. So think about what you have to do. All the elements that you require are here. Think about you should have what you should do. Right? Okay. So let's move on. Shaping works we did. Then there is something called as a clipper. Just to finish the various kind of diode circuits, right? There is something called as a clipper. So what does a clip circuit do in here? From the word, what do? So a clipper, for example, takes that as the input and ends off, right? It clips it. So for example, you can have a circuit which clips the positive part to some value. Okay, I can call this, say, V plus, and then say it comes and clips the negative part to some value. Okay, and then some that, and say this is V minus. Okay, in fact, we have already looked at a very special case of this. Exactly, right? A half wave rectifier. What is the value of V plus and V minus for that? V minus is 0 and V plus is very high, so it's come through, right? How did we draw the half wave rectifier? What did we have? We had a diode and a resistor. So this was a rectifier, right? So from this, how do you get a clipper? Right? You have to do something, right? So you have to add some voltage basically. You have to add some DC voltage. I'm not think of it. Okay, we'll put a tutorial and give you the clipper. Okay. With that, basically, we have done a whole lot of circuits. So what did we start with? Right. So we started off with rectifiers. We'll go back now to rectifiers. Okay, and design one. So we looked at the half rectifier. Then you looked at the full wave rectifier using two diodes. Then you looked at a peak detector. Peak detector has diode and capacitor, right? Then you looked at the negative peak detector. Okay. Then you looked at a clamp. Basically, same circuit of diode and capacitor, but taking the voltage across the diode instead of the capacitor. Okay. So diode plus capacitor gives you either a clamp or a peak, right? Then we looked at this voltage, and then I said that you cascade these things and make a multiplier. Okay. It's an interesting circuit to analyze, and I'm going to be nasty. I'm going to discuss it here. It will be in your tutorial. Okay. Have some fun with it, and we'll think about whether we should spend some time on it. Okay. Put in the tutorial. Yeah. First tutorial. Then AM detection. I also mentioned that peak detection is a method to remodulate signals, right? And I haven't finished it here. It will also be in your tutorial. And then we went to these diode shaping networks. All right. And finally, I left you with the clipper, and I have you to think about it. Decreasing part. Which decreasing part? Yes, it will. Because what you're plotting here is only a function of time. It is not the special case we talked of in the previous plot. Here this is voltage is function current, right? Here I am just plotting voltage is a function of time. So that issue of resistance is not coming here. Think about this. If I do the whole thing here, then it will appear absolutely clear to you in the class, and then when you do it yourself, you will not have an idea as to how to proceed. Okay? So it's good you spend some time on this. Okay. So these are basic circuits, diode circuits. There are infinite number of them, which we haven't talked about. But with these, you get a feel for what is happening, right? And you're able to design various diodes or analyze diode circuits. Okay. Just to close this, the clamp and the peak detector had a diode and a capacitor, right? And maybe some battery to do some offsetting, right? The clipper and the rectifier basically have a diode and a resistor. So diode and resistor combination does some diode and capacitor combination does something else. Okay, all right. So now I'm going to close this here. Any questions? And we move to more important but related to what we were doing so far, which is design of DC power supplies. Okay. So far, remember, we haven't talked about the Zener mode of operation, right? And I mentioned that is used for voltage regulation, but let's not worry about that for now. We'll do the DC power supplies, and then at the end of the DC power supply you need a regulator. So when we're doing that, we will try and finish the Zener operation also. Okay. So hopefully by tomorrow I will get done with the diodes, so that from Monday we will start with amplifiers. Okay. We have a lot to do. The diode part is the easy part. In the IIT Madras course, they don't do the diode part at all, which I thought was not nice. In some of these, at least you know that you can do all of these things, right, with diodes. Okay. So as I mentioned earlier, we discussed what the basic structure power supply is going to be, right? You have some kind of a transformer, then you go to a rectifying stage, you go to a filter, and then you have a regulator. Okay, that's the basic knowledge. We proceed. Right? Just think about the following. Let me say that I have, say I start with a transformer. Say this is an N1 transformer. And say I take this, pass it to, okay, and say I pass it through a capacitor. Okay, and let me, my input here is Vp. To make this, let me say the input is N times Vp sine omega t. So that voltage here becomes Vp sine omega t. Okay. Otherwise, I have to introduce another variable. Let me say I have this. Okay. What do you think the voltage across capacitor will be? Right. So now let us be careful. I am taking the full voltage across a capacitor. So it's small v, capital C. Okay. And just to have some fun, let me say I have sinus as the input. I think I should save like a sinusoid in my favorites. I keep drawing. Okay. Let me say that is the input, and what is the output? Right. This is basically a peak detector, right? So it's going to will hold till there, and then okay. So it's a good power supply. This is also a good DC power supply, no? Instead of the half-wave rectifier, was the half-wave rectifier circuit at this resistor instead of this capacitor, right? You look at this circuit drawn here. Look at them and look at this one. What's the difference? So of the resistor you have a capacitor, right? So this is another way of making a nice DC power supply, right? Because in this situation you will get only the positive half cycles, and then you have to iterate and all of that. If you use the resistor, use the capacitor, you directly get the peak value, and it's going to hold at that value. All right. So then shall we just close and go? What's the problem? Why do we have to still worry about this? Why will there be a slight slant? Still, it's an ideal capacitor. Okay, but still it's an ideal capacitor. Alright, so then the input, okay, I guess saying. So if there are fluctuations in input voltage, the output voltage will track the input voltage. If say from Vp sine omega t it becomes 1.1 Vp sine omega t, the peak detector, so it will no longer sit at Vp, it will go to 1.1 Vp. Okay. Then, but what do you want to do with the power supply? You want to drive a load, right? You want to drive a load. So I am going to connect now. A load RL. So now, the moment you connect a load, what will happen? This capacitor will discharge. Correct? So now you can see that if you go back to your rectifier, right? If you take the half wave rectifier which had a diode and a resistor, to fire it you would have to put a capacitor. Or another way of looking at the circuit is start with a peak detector and then you connect a resistive load to it. Okay, both the two ways of just looking at the same circuit. Okay, so yes, now once I have this, it's going to discharge. So how will it discharge? How will the discharge appear? In which region will it discharge? So in this region, what is the state of the diode? Diode on or off? On, right? Diode and then subsequent diode is off, right? Subsequently diode is off, because once this thing, assume the resistor is not there, right? Once it gets charged to Vp, the diode will no longer turn. When will it turn on? Yes, right? Once the capacitor discharges, will it turn on immediately? Think about that. Think about that. What Shiva got the point. It will discharge, right? So you're going to discharge from here. So the diode is off in this region. Now I am connecting the resistor back, right? So you're going to discharge from here. Diode will remain off all the way until in this region your diode is going to remain off. It will turn on the moment your voltage goes more positive than the capacitor voltage. Basically it will turn on this particular point gets more positive than that particular point. When the node becomes more positive than the cathode, the diode will turn on, right? So you will have a characteristic which is basically like this. Then, so maybe I should have some other fancy. Okay, so it will be okay, and then go up, right? Will it follow which one exactly? Right. So after you come here, right? Yeah. So it will be. What you're saying is correct. Won't exactly follow, but let's assume that that's going to happen. There is a time constant associated with that also, but assume that no. Crudely, it's okay, because we'll make this particular. We'll make an approximation now. Okay, which will make the analysis very straightforward. So, how should you design now the capacitor? What should be the value of the capacitor you put? Alright, to answer that question, you can tell me. Okay, you tell me what is this expressly given by? Say this is Vp and say that I am going to measure the time from here. Okay, this is T prime. T prime is measured from the peak. Okay, so this will be Vp e power minus time by Rc, correct? Where your Vp is this. Would you use your charge with respect to what? Good, right? Basically, you don't want this to discharge significantly. That means its time constant must be really large, right? If time constant is very large, then your discharge will not be very significant. And whenever I say small or large, it's always with respect to something. What is your time scale in this problem? It is you have a Vp sine omega t, right? So you have a time period corresponding to, right? This is your 2 pi by omega, right? So basically you want your design should be you want Rc or Rn to C must be greater than time period, and greater than means 10 times, right? All right. And what's the value of DC then? What is the value of the T component roughly? What is the DC value? Vp, yes. Okay, because you put this capacitor there, you don't worry about Vp by pi and 2 Vp by pi and all of that. It's roughly Vp. Okay, now if you have RLC greater than T, what can you do to this exponent? Is there an approximation you can do? That will close. Right? So your Vp essential minus T by Rc, right? T prime by Rc is Vp into 1 minus T prime by Rc. Okay. Now I want to find out how much voltage actually dropped. I want to find out this. There's a name for this. We mentioned it earlier. This is your V peak to peak okay. So what do you think your V peak to peak ripple is going to be? And then I'll close. So your V peak to peak ripple is going to be roughly years Vp T dash by Rc. What is T dash? Right? So what you're going to say is that yes, I want to find out need this particular time, right, when this thing actually comes and hits, but I don't really care. I'm going to say that this time is approximately equal to the time period of the signal. Okay, that makes sense, right? Very crudely. It's good enough. Okay, so basically this is going to be Vp into T by RL into C. Okay, good enough, engineers. So as a problem, do this and we'll continue tomorrow. Have a signal, okay, which is like this. straight line goes up, straight line goes up. Okay, this kind of sawtooth form. Say this is V alpha. Okay, and say this is. I want you to find out what is this value.